Alright, so in our first set of notes, we did a kind of like 10,000 foot level understanding of probability. We want to kind of start taking that down to get to some specific numbers. So we're going to build a probability model, right? So we're into like, how do I get a theoretical probability that I can use to do computations with without having to do the experiment, right? So when you build a probabilistic model, sometimes called a probability distribution, you end up with like a two-column list, right? The first column of the list is a list of all the possible outcomes. And this could happen, this could happen, this could happen. And the second column of the list is all of the probabilities for those outcomes. So if you have the list of possible outcomes in the first column and the probabilities for each of them, those probabilities should all add up to 1, right? So if you have all the outcomes, then it should add up to 1. Now, that means the left-hand side is the list of all the possible outcomes. We have a name for that. We call that the sample space. That's the space out of which all of the outcomes could come from. It's a little bit of a weird term because it's like, ooh, okay, it's the space that we sample from, right? Okay. If I am combining a set of those outcomes, right? So I take a group of those outcomes and I put them all together. That's what we call an event, okay? And we can get a theoretical probability for that event so long as each of the outcomes in the sample space has an equal probability of occurring, right? So kind of think of this as like the outcomes in the sample space are like the atoms. You put the atoms together and you get like different molecules, which we're going to call events, right? And each of those little atoms, or each of the outcomes in the probability model, we would like to think of having an equal probability of occurring. So this means that if I take the total number of outcomes in the event, right, and I divide that by the number of outcomes that's in the sample space, then, so this is a counting thing, right? Count how many outcomes are in the event, count the number of outcomes in the sample space. That should give you the probability of that event given that sample space, right? So note, if S is the entire sample space, so you could have an event that like something in the sample space occurs, well that means that the probability of S is 1, because if something occurs, it should be in the sample space. Okay. Something that's useful here is this idea of a complement. So every event has a complement. It's basically the event is a collection of outcomes in the sample space. The complement is the collection of outcomes that are not in that event, right? So it's like the complement is all the outcomes where that event does not occur, right? So you could look at it as either the event or not the event, right? So it's either the A or the complement of A, which means that the probability of the complement of A should be 1, the probability of the sample space, minus the probability of A, right? So because the complement and the event should add up to 1. Cool. We have events that are mutually exclusive, okay, which means that when one event occurs, the other one does not. Okay, so these two events cannot occur at the same time. Okay, so it's like the probability of being a square and a circle, right? These are, you can't be both, a square and a circle, last time I checked. So the way we define this is we say that events are mutually exclusive in that they have no outcomes in common, and another way of saying that is that the probability of both of them occurring at the same time is 0, right? Okay, so you have to be careful here. Mutually exclusive means that they cannot happen at the same time, or do not happen at the same time. They have no events in common. Doesn't mean that it spans the entire sample space, right? So yes, an event and its complement are mutually exclusive, but not all mutually exclusive events are complements. So keep that in mind, okay? So if you add up two mutually exclusive events, you don't necessarily get a probability of 1. But if you have the probability of two mutually exclusive events occurring at the same time, that has to be 0. Now, that gives us a nice, neat situation because there's no overlap. There's no both happening at the same time. So the probability of one of them happening or the probability of the other one happening, right? So the probability of one of these two mutually exclusive events happening is just the probability of one plus the probability of the other one. Okay, so that's what we call, it's an addition rule for mutually exclusive events, but it's just like really just, it's a special case. Most sets of events have some overlap. Okay, so they have something in common. Okay, in that case, like the I randomly choose a student who takes Algebra 2, and I randomly choose the probability of choosing a student who's taking Algebra 2 and the probability of choosing a student who's a 10th grader. Okay, so those are not mutually exclusive events because you can be a 10th grader who takes Algebra 2. Those happen at the same time. So there's overlap there. So what we got to be careful here is when I'm doing the OR, like the choice of choosing a 10th grader or choosing an Algebra 2 student, I don't want to count the people who are doubled or that do both twice. So I have the probability of being a 10th grader, that's 1. The probability of being an Algebra 2 student, so that's like add those together. But now I've counted the 10th graders who take Algebra 2 twice in that model. So I have to subtract out where they overlap, right? So I have to subtract out the number of 10th grade Algebra 2 students because I've counted them twice. Now you're going to note that like these two things are actually this the addition rule for mutually exclusive events is really just a special case of the general addition rule. And why? Because the probability of mutually exclusive events occurring at the same time is 0, so this last minus p of a and b, well, that's 0 anyway, which just causes you to drop back to the rule for mutually exclusive events. So if you think about that a little bit, they're really saying the same thing. It's just that one is a special case of the other. All right. One of the ways that we make sense of this is using a Venn diagram. So you're used to Venn diagrams. You've seen them in English class. Sometimes we've used them in math classes. Venn was a mathematician, so they stole it from us. But you like use them to make like comparison contrast essays or something like that. It's whatever. But in math, the way we look at it is the rectangle is the sample space. It's the set of all possible outcomes. The circles are events. They're sets of outcomes that are grouped together. If the circles have overlap, then it's possible for both events to occur at the same time, so they're not mutually exclusive. Mutually exclusive events would look like two circles that don't touch each other. They mutually exclude each other. Like if you're in the A crowd, you cannot be in the B crowd because the A crowd does not want you in the B crowd. And if you're in the B crowd, you can't be in the A crowd because the B crowd does not want you in the A crowd. So they mutually exclude each other. They're like, oop, nope, you can't be with us because you're in the other group over there. Like, you've probably met some groups of people that are mutually exclusive in your life. All right. However, if they're not mutually exclusive and they have that piece in the middle where you can be both A and B, then you say you're in the intersection of the two groups. Okay, so you can be both a 10th grader and you could be in Algebra 2. You would be in the intersection of 10th graders and Algebra 2 students. Right, so what we do there is we call that the intersection. That's the A and B. That's denoted with this A upside down U, B. Sometimes we call that A cap B or A intersect B. The symbol is called a cap symbol. It's kind of cute to see it that way. It's like a little hat that people put on. So A cap B. Union is different. Union is just like you're in one of the groups or both at the same time. So like if you're in like A or B, you could be in A, you could be a B, or you could be in both A and B. which is a little bit different than the way the English language deals with this, but in math we let you be in the intersection and still in the union at the same time. So union means I'm in an A, I'm in B, or I'm in both. It's all good. We denote that with a U B. So it's an A with an upside or a right side up U. With a B, you can read that as A union B. Sometimes it's called A cup B. So the upside down one is called cap. The right side up one can be called cup. But sometimes people just read it as A union B. So note, you could take like this addition rule that was back here where we had ors and ands, and you could take out the or and you could put a cup in there, and you could take out the and you could put a cap in there, and you say the probability of A union B is equal to the probability of A plus the probability of B minus the intersection of A and B, where you could say probability A cup A B is equal to A probability of A plus the probability of B minus the probability of A cap B. Cool. Whatevs. All right, so theoretical probabilities are dependent upon identifying outcomes that are the result of a chance process, and then breaking those into collections that we call events. Using these the basic rules, you can calculate the probability of an event, its complement, and the probability of the union of two events, right? So that like either A happens or B happens or both happen. And that's going to be the probability of A plus the probability of B minus the probability of A intersect B. Unless they're mutually exclusive, then the probability of A intersect B is 0 anyway, so then it's just the probability of A plus the probability of B. Alright, so we're going to use this in the next class or so. I just try to make some sense of it, but we're back to numbers and doing quantification of probability. Alright, see you soon.